Assalamu alaikum and welcome to lecture number 20. In this lecture we are going to discuss about the locations of the zeros for FIR linear phase system. This is the last topic of your of this chapter. We are following the book that is Discrete Time Signal Processing by Alan V. Oppenheim, and most of the figures, numerical problems, they are taken from this book. So this will be the last topic. We will also discuss a brief summary of the topics we have covered in this section, and you are expected to have many questions. So I hope you will have many questions and many things to discuss in this lecture. In the previous lecture, we talked about the properties of the impulse response and the frequency response for all the four types of FIR linear phase systems. For the case of the even symmetry, that is type 1 and type 2, we know h of n equals to h of m minus n. So the z transform of h of n resulting into system function will be h of z equals to summation n running from 0 up to m, h of m minus n, and you understand that's the impulse response, and you multiply it by z power minus n, so you get the system function. Now this is equal to summation k running from 0 up to m, h of k, z of k, z power minus m. Maybe you understand that we have changed the variable of summation, and which will result into this expression, or maybe I just tell you how you can change the how you get this expression from this one. So you understand that we replace the variable of summation. So if I say let k equals to m minus n, so that means n equals to m minus k. So putting in this equation, okay, when n equals to 0, when n is 0, so putting 0 here, k will be equal to m, and when n equals to, the upper limit is m, so when n equals to m, that means k equals to m minus m, which is 0. So when n equals to 0, k equals to m, when n equals to m, k equals to 0. So that means replacing values in this equation, summation n running from 0. So when n equals to 0, we have k equals to m. So k equals to m. When n equal, for the uppercase, you understand it will be 0, because when n equals to m, so you replace n by m, so m minus m will be 0. Again, h of m minus n, so m minus n is basically k, so h of k, z power minus m minus k. Okay, so that means you understand in summation you can change the limits, interchange the limits, because in case of integration you have upper limit minus lower limit, right? But in case of summation we just sum them, whether we sum it from k running from 0 up to m, k running from m up to 0, or we sum it k running from 0 up to m, it results into same. So that means k running from m up to 0 is same as k running from 0 up to m. So k running from 0 up to m, again this is h of k, and because this is z power m minus k, so when you open the bracket it will be z power minus m minus plus k. So that means we have z of k into z of minus m. So because z of minus this term, this is independent of k, so we can write it as z of minus m, where is summation k running from 0 up to m, h of k, z power minus k. So this is similar to the z transform equation, which is this one. So you understand we have just change of variable doesn't affect. If we have n, then we have n running from 0 up to m, h of n. If we have k, then we have k running from 0 up to m, then we have h of k. Now if we look at the standard equation, this is equal to h of z. So because here the multiplier, we are multiplying with z power k, so that means basically this is z power minus 1. Okay, so we are summing it into over z power minus z inverse, right? Because z power k can be written as z power minus 1, right, into minus k, so that will result into h of z inverse. I hope that's pretty straightforward. So we get this expression, we call it equation 1. So from equation 1, if we have z naught 0, right, we have a 0 at z naught, so replacing h of z by z naught, we'll get h of z naught equals to z naught power m, z naught power minus m into again z inverse, so it will be z naught inverse. And because we say that z naught is 0, so that means you understand pole 0 things, that 0 is when you put some value of z, and that results in which h of z results into 0, so that will be 0. So we say this is 0, so that means h of z naught will be equal to 0. So if we say z naught equals to r e j theta, right, and you understand this is 0, so that means when z naught r e j theta is 0, the reciprocal of this one, that is z naught inverse r, right? So if you invert it, it will be 1 over r and 1 over j theta. So 1 over r can be represented as r power minus 1, and 1 over e j theta, because in case of the angle, we just, if it is in denominator, you bring it to numerator, it will just interchange the sign. Or in general, you understand for the exponential thing, like anything power something, right, when it's 1 over, so when you bring it to numerator, the sign of the power changes, or if it is in numerator, you bring it to denominator, then again its sign is changed. So that means we just get r power minus 1 e power minus j theta, and again this is also 0. Okay, so when h of n is real and each complex 0 not on the unit circle will be part of the set of 4 conjugate reciprocal zeros of the form, because you understand in previous slide we said if z naught is 0, then we have two zeros, right, one at z naught and one at 1 over z naught, because h of z was equal to z power minus m and into h of z inverse, right? So we have, so based on that we can say the z naught is 0. So when z naught equals to, for example, r e j theta, then we have conjugate reciprocal of this one, so we have r 1 minus r e j theta z inverse into 1 minus r e j theta minus j theta, right, because they will be in reciprocal conjugate reciprocal pairs. Okay, so again for the second part where we said if z naught is 0, then 1 over z naught is also 0. So in case of 1 over z naught, then we have two conjugate reciprocals, if they provided they are not on the unit circle, then we have for that case 1 minus r e j theta z inverse into 1 minus r e j minus theta, right, z inverse. In case zeros are on the unit circle, so you understand when they are unit circle means r equals to 1. So when something is on unit circle, r equals to 1, and if this is the case, then we have the z transform equal to the discrete time Fourier transform. So in that case we will have zeros in conjugate pair, so we will have 1 minus e j theta z inverse and 1 minus e minus j theta z inverse. The other case is if 0 is real, right? So real means and not on the unit circle. The reciprocal will also be a 0 of the h of z, and will have factors of the form 1 plus minus r e j theta z inverse and 1 plus minus r e power minus 1 e power j theta z inverse. So you understand, because if it is real, then this part is e j theta will be 0, right? So theta is 0, so this will become 1. So again, this is, then we have reciprocal of this one, so we have something like 1 plus rej theta z inverse. So we have 1 plus minus r z inverse and 1 plus minus r inverse, you understand from the derivation we did on the previous slide. So it will be 1 plus minus r inverse z power minus 1. If 0 is at z equals to plus minus 1, so it can appear all by itself because it's its own conjugate, so that then we can write that h of z will be of the form 1 plus minus z inverse. So in case of even symmetry that we have for the type 1 and type 2, when z equals to minus 1, so that means h of minus 1 equals to minus 1 power m h of z in okay, 1 over minus 1, so 1 over minus 1 is basically minus 1. So we have this expression when z equals to minus 1. So again, this expression depends on the value of m, so you understand minus power m means if m is odd then it will result into minus 1, and if m is even then it will result into plus 1. So that means for even value of m, h of minus a h of minus 1 will be equal to h of minus 1. So that's fine. So that means simply we have the identity system, right? But in case m is odd, so that means for odd value of m this will have minus 1, so h of, right? So that means we will have something like this, h of minus 1 will be equal to minus h of minus 1. So this is only possible when this is equal to 0. So that means the system function must have a 0 at z equals to minus 1, because only for the 0 case h of minus 1 will be equal to minus h of minus 1. Okay, in case of impulse response is anti-symmetric, that is type 4 or type 3 and type 4, so we can express h of z as minus z power minus m h of z inverse. I hope you can derive this expression by yourself. I have done it for type 1 and type 2, and you can do it for this case. So based on this equation, we can say that zeros of h of z for the anti-symmetric case are constrained in the same way as the zeros for the symmetric case. Now if z equals to 0 is a 0, in that case we can say h1, right? So you just replace that with 1, so h1 of z equals to minus 1 power minus m, and it will be hz inverse, so this is 1 over 1, which is 1, so it will be equal to minus 1 power minus m into h of 1. So that means it will be equal to minus h1, right? So h1 equals to minus h1, so that means it's the only possibility that h of z must have a 0 at z equals to 1, right? Irrespective of whether m is even or odd, because whatever value of m is even or odd, because minus is here, so it will always result into minus 1. So that's why we can straight away write that h of 1 equals to minus h of 1. So the second case is when 0 equals to that is z equals to minus 1. So you replace minus 1 here, so it will be h of minus 1, and again minus 1 power m, h of 1 over minus 1, so h of 1 over minus 1 is basically h of minus 1. So that means we have the resulting expression minus 1 power minus m plus 1 h of minus 1. Okay, simply you can say that this is minus 1, so minus 1 multiplied by minus 1 power minus m, so you see the bases are same, so power will be added, so we can write minus 1 power minus m plus 1, and again from here we get h of minus 1. So we have this expression. I hope this is quite straightforward. So that means if m is even, so for the case of even, straight away you can also tell from here, if m is even, this will be plus 1, and there's always minus 1 multiplied, so it will result into minus. So we will have h of minus 1 equals to minus h of minus 1. Okay, so that means there must be 0, right? This is must. So in case m is even, right? So the first case was when m is odd. In the case of odd, uh, we'll have m plus 1. So m plus 1 will result into even, and h of minus 1 will be equal to h of minus 1. I think that's quite straightforward. So in A and B, shown are the typical 0 locations for type 1 and type 2, whereas shown in C and D are the locations for the locations of zeros for the type 3 and type 4. These constants on the zeros are important in designing FIR linear phase systems, since these impose limitations on the types of frequency responses that can be achieved. So with this, the chapter on transform analysis of linear time invariant systems conclude. The main topics that we have covered in this course: the frequency response of an LTI system. You understand that frequency response of LTI system is often characterized in terms of the magnitude response, phase response, and group delay. Linear phase is often desirable characteristics of a system frequency response, since it is relatively mild form of the phase distortion, which corresponds to the time shift. The systems characterized by linear constant coefficient difference equation. You understand there are different representations of the LTI system. One of them is the linear constant coefficient difference equation, and discrete time filters are most typical implementation of the linear constant coefficient difference equation. We also talked about the frequency response for a rational system function. We express the magnitude in dB, and we also talked about the phase and the group delay. And I hope you understand and have clear concepts about this topic. But anyway, if you have confusion or you want to discuss anything regarding any of the mentioned topics here, we can discuss it in the live session. And we talk about the relationship between magnitude and phase response, and we know that in general, knowing magnitude response of the LTI system provides no information about the phase. However, for the system described by linear constant coefficient difference equation with some constraints, constraints between the magnitude and the phase. In particular, if the magnitude of the frequency response, the magnitude response is given and the number of poles and zeros are known, then there are only a finite number of choices for the associated phase. Similarly, if the number of poles and zeros at the phase are known, then within a scale factor, there are only finite number of choices for the magnitude response. Similarly, in case of all pass systems, the magnitude response is independent of frequency, numerator and denominator factors are complex conjugates of each other and therefore have the same magnitude. So in short, we can say the frequency response is constant in case of all-pass systems, and it is same for all the frequencies. Next topic we discussed was the minimum phase system. In case of minimum phase system, we said that all the poles and zeros of the system will be inside the unit circle. So such a system is called as the minimum phase system. In case of minimum phase system, both the original system and the inverse system, they both have all the poles and zeros inside the unit circle, because in case of inverse system, you have studied that the inverse poles of the original system becomes the zeros of the inverse system, and similarly the zeros of the original system becomes poles of the inverse system. So if the original system is stable and causal, so because in this case there are no restrictions on the positions or places of the zeros. So if the original system is minimum, that means all the poles and zeros are inside the unit circle. In that case, the inverse system is also causal and stable. So in case of minimum phase system, the frequency response or the magnitude, or simply the magnitude response, specifies the phase uniquely, and the frequency response phase, or we also call it the phase response, specifies the magnitude to within a scaling factor. The last topic we covered was the linear systems with generalized linear phase. We have done during this chapter different examples, and we saw that the effect of linear phase with integer slope is simply time shift. Similarly, a non-linear phase, on the other hand, can have a major effect on the shape of the signal, even when the frequency response magnitude is constant. Thus, in many situations, it is particularly desirable to design systems to have exactly or approximately linear phase. So we define a generalized linear phase system as a system whose frequency response is real valued non-negative function of omega, which is frequency, multiplied by the linear phase term. So with this, we define four different types of the linear FIR systems. Type 1 system, which is defined as a system that has a symmetric impulse response, with m being an even integer. Similarly, there was another type that is called type 2 linear system, which is also symmetric, which also has a symmetric impulse response. In this case, m is an odd integer. Similarly, for the case of type 3 and type 4, we said these are the anti-symmetric cases. And in case of type 3, the system has anti-symmetric impulse response and m is even, whereas in case of type 4, m, the impulse response is again anti-symmetric and m in this case is odd. So the last topic we covered was the locations of the poles, locations of the zeros for FIR linear phase systems. So we end the lecture here. Yes, of course, it's a short lecture because then normally we have, but because you have a sessional week, this is your sessional week, so that's why we conclude here, and we'll start the next lecture with the new topic, new chapter. So Allah Hafiz.